Welcome to Quantum Photonics. So today's episode addresses the question is of are ideas contagious? It touches on how both diseases and information spread through human interactions. So this study, which our speaker will be talking about later, explores how the structure of social networks affects the transmission of both illnesses and ideas, focusing on two types of contagion, simple and complex. Simple contagions spread directly from one person to another, like a virus. Complex contagions, on the other hand, require a person to be influenced by multiple people in their network before they catch the idea or behavior. Maybe we can also relate to this, asking ourselves, how is the social contagion happening in Clubhouse, especially now and also before when we were on lockdown and, trying to make networks among people and spread ideas. So these researchers in the study, as you will see, there is a paper here on the room chat that you can check also later on. This is the work of our speaker. They developed a new method to better understand these dynamics by reconstructing social networks based on how different ideas or behaviors spread. Their model challenges the traditional view that contagions can only be simple or complex and allows for a more nuanced approach. So, I'm very proud to introduce our guest speaker, Nicholas Landry, who is an assistant professor of biology at the University of Virginia. He leads an interdisciplinary lab which studies how the structure of networks and groups affect the spread of diseases, information, and ideology. The Landry Lab uses tools from dynamical systems, data science, Bayesian inference, and open source software to investigate these questions. Nicholas is also passionate about open source software and founded the XGI and hypercontagion software packages as tools for analyzing the structure and dynamics of these higher order networks. Prior to joining UVA, he completed a PhD in applied mathematics at the University of Colorado Boulder, and then he was a postdoctoral research fellow at the Translational Global Infectious Disease Research Center, TGIR, in Vermont Complex Systems Institute at the University of Vermont. So, without further ado, I bring to you our guest speaker, Dr. Nicholas Landry. Nicholas, welcome to Quantum Photonics.
Thanks so much for having me, and thanks for the nice introduction. I'm so happy to be here. Um, I was kind of thinking about what I wanted to talk to you all about, and I heard something last week that was contagion actually comes from the Latin root, which is con, which is with or together, and tangere, which means to touch. And so I think when I picture contagion in all of its forms, whether it be information or pathogens or whatnot, um, it all comes down to human connection and how we're connected to one another. So, most broadly, I think about how people are connected and how that affects how diseases, information, and ideas spread. And so if you look at slide one in the slides that Cecile shared with you all, I think about complex systems. And so complex systems kind of tell us how societies are organized, maybe how fireflies synchronize, etc. And it just simply refers to a group of individuals or agents in a population, and we actually care about how they interact with one another. In complex systems, we think about emergence, how the sum of its parts, or the whole is greater than the sum of its parts kind of ideas. And that's true in contagion. So if you look at slide one, we've got this group of people, and they can be connected in different ways. And so I study a specific type of complex systems known as network science. And so if you go to slide two there, um, networks are basically, we make this assumption that in a population or a society, that two people can interact at once. If you want to talk about some of the limitations of that approach, I'd be happy to talk about it after. And basically, we get an abstract representation of the world where we've got people represented as nodes and the connections between them as edges or links, are what people commonly refer to these as. And so this really is a effective way to kind of model how society is organized and how pathogens spread through a population. And so if you go to slide 3 here, the reason why I want to bring this up is because this might be the paper that changed my life. Um, I was not totally sold on the idea of network science. Um, but this paper, if you look at this slide, what they did is if you're on slide 3, in panel D, what they tried to do is they looked at H1N1 and they looked at SARS. And what they did is the country of origin is at the origin of the plot. So, for instance, for H1N1, it's Mexico. And for SARS, it's China. And what these researchers wanted to do is predict when diseases would appear in other countries. And you can see when you just plot it compared to geographic distance, it looks like a random scatter plot. Okay? So this seems to indicate that it doesn't really matter how far you are geographically to when a disease will appear in your country. But what these researchers realized, which I think was so cool and is why I like this paper particularly, is because they realized that flights are how we get to different countries. Okay. And so if we look at a different kind of distance, a network distance, where if you go to slide 4, we calculate the distance to countries by how long it would take on a plane and the volume of people traveling between those countries. If now you look at panel D, it looks like a much better prediction. And so this is kind of my pitch to you why networks matter. Networks affect how contagion flows through a population. People who are very popular or maybe have a lot of connections tend to be the hubs and they are very influential in the spread of disease. In fact, there's something in network science known as the friendship paradox, which states that on average, your friends have more friends than you do. And this kind of idea is the same kind of thing that allows us to better understand how diseases spread when we think about networks. So that kind of sets the stage for what I want to talk to you about today. And if you go to slide 5, this is the central question that I want to ask. So think about a population right here in this illustration. I've got a group of people that are linked up to one another. This is actually a famous example in network science. It's called the Zachary's Karate Club. It actually is formed from surveys that a social science researcher did, and it actually turned out that in the middle of his experiment, the group split, and so you can kind of see these two different communities here. Um, but we're using the Zachary's Karate Club to illustrate a point. So suppose I've got this social network. Based on who is connected with whom, I might get a time series. So a time series just refers to at each time I look at who's infected and who's well or susceptible. And as I move forward in time, I keep surveying my population and I see when they get better and when they're infected. So it might look like something on the right hand side here. So for each of these nodes or people, when I've got a black square, it indicates that at that time, that node was infected. Okay, and so we can look at this over a bunch of time steps and look at it over, maybe a year or something, and we get a time series that looks like this. This is what's known as the generation step or the simulation step. So basically, the idea is if I know what the population is, how will the disease spread on it? But the thing is, we can also ask the opposite question, which is if I know how the disease spread, maybe it's with contact tracing, maybe it's with surveys online, maybe it's hashtags on Twitter. We can actually ask the opposite question, which is if I observe this series of infections or opinions or whatnot, can I actually figure out what's the most likely network to have created that time series? And that's the question that we are asking today. And so, kind of the idea here is we're actually working with our what are known as matrices. So it turns out that every network we can represent as a matrix, which you see here in the bottom left. And so basically, think about it this way: if I've got in row J and column I, if there's a black square, that indicates that node I and J are connected. And notice that it's symmetric because there's no inherent direction to these friendships, unlike you might see, for instance, on Twitter, where you can have followers, but maybe they don't follow you back. So we're going to be working with these matrices in the future. So just kind of keep that in your mind as we move forward. So now I'd like you to go to slide 6, and I'd like to describe the different types of contagions. Cecile did a great job at giving an introduction here. So what I'd like to say is that simple contagion is what a lot of people in epidemiology use to model pathogenic transmission. So the idea is I only need one person to get me sick. One example of this is if I've got a node J that's infected with a probability beta, so I'll like flip a coin, and if it comes up heads, I will infect a susceptible or not infected node I. Um, and so on the flip side, when we think about how behaviors spread, or maybe how ideology spreads, we get what's known as complex contagion. And complex contagion just refers to the fact that one person telling me about some trend or some fad might not be enough to convince me. In fact, with the election coming up, maybe there's some political issue that I need swaying on. And there's this kind of push and pull effect where if a critical threshold of my friends uh, believe a certain thing, they can convince me. And in the social science literature, one of the most common models here is the threshold model. So basically, the idea is I look at all my friends and I say, how many of them believe this certain thing? If it's above a certain number, or in some cases, a certain fraction, then I will also adopt that opinion. So, for instance, in this diagram, we've got 3 out of 7 of the neighbors that are infected or believe a certain thing. And so if the threshold was 2, I would adopt that opinion. But if it was 4, I wouldn't. So the interesting thing here, though, is in a lot of the literature, people treat these two things as dichotomous. So the idea is that, oh, it's either simple or it's complex. That might not be the case, though, because there's been some work done many years ago that we're rediscovering, actually. So if you go to slide 7, it turned out, and this is often true in science, when you want to do something, someone's done it about 40 years ago. And it turns out that in the original paper by Granovetter on threshold models of collective behavior, he defined this neighborhood based model. Okay, so the idea is very simple. Basically, just like in the complex contagion case, I'm still going to survey my neighbors and I'm going to count how many of them are infected or hold that certain opinion. And the idea is if you look on the right hand side, there's 2 special cases for how I can uh, describe functions saying how the number of infected neighbors translates into the probability of infection. And because these are 2 special cases, we can think about them as 2 ends of a spectrum. And so the idea is that maybe uh, some kind of contagions are neither simple nor complex. Okay. And we want to do more work on this. And we're still in the process of making this happen. So we're going to use this. Go to slide 8. to try to reconstruct networks. And we've got our Zachary Karate's Club network, like we had before. And on the left-hand side, we've got the ground truth, or what we know to be the true network. And then what we're going to do is we're going to run some contagion processes, get a bunch of people infected, and say, how well can I recover that original network? So what you're looking at here is, so if it's a black square, that indicates that it's a 0 or there's no connection. If it's a light blue square, that indicates that it's a 1 or there is a connection. So if I did perfectly, I would notice that all the matrices in the middle and on the right-hand side should look identical to the one on the left. And that's not quite the case. What we see in the simple contagion case, this middle panel here, is notice there's some purple squares. What this indicates is that half of the time we get it right, half of the time we get it wrong. And notice also, I've illustrated with red squares here. There are some places where the simple contagion process seems to learn the network better than the complex contagion process, and vice versa. So I've just told you this, but the question really is, what types of network structure, if I look in a real population, what kinds of structures can I learn best? How can I most effectively learn the network of transmission if I've got some data on who was infected when? And now I'd like to go to our final slide. I'd just like to talk about this for a little bit. There's a lot of information on this slide, so I just want to walk you through it. So if I look at the figure here, on the top row, we see some random models. They're basically, we create some synthetic models of population structure. So we've got this Erdős-Rényi network, which basically says connect two people at random. It may not be a good model for how people are connected, but it gives us some sense to the effect of the density of connection. Secondly, we look at what's known as the power law configuration model. What this does is it just says, let's vary how popular the most popular people are. So this basically measures the heterogeneity in the way people are connected. So some people might be connected quite a bit, and some may only have, say, 1 or 2 friends. And we kind of notice that in this little diagram here. We see some nodes on the edges, they're only connected to 2 people, but in the center, they're kind of like hubs. And then lastly, we see for the clustered network, this looks at the effect of cliques. Like if I've got a clique in a friend group, how can I expect that that will affect how contagion is spread, and then also how I can recover it. Okay, and so now what I'd like to show you is that these red portions of the plots, again, we're on the last slide here. This indicates that complex contagion, so think ideologies, opinion spreading, etc. That is where I actually recover the network better than simple contagion. In these light blue regions, this is actually the opposite. It's where simple contagion outperforms complex contagion. And then in black, this is where we perform about the same. And one more thing I want to alert you to is maybe you've heard of R naught. R naught is simply, on average, the number of people that an infected person will infect. Okay? And so that's actually a good proxy on the whole, I would say, for how contagion is spreading. There are some limitations. I'd be happy to talk about it after. But yeah, we've got basically where between the structure and dynamics, we have equal R naught values. We've got these gray kind of curved lines. So kind of our takeaway from this was that it turns out that R naught is the only predictive thing in whether you can recover your network or not. And this kind of makes sense because when you have a R naught that's high enough, you actually have very saturated dynamics. And because everyone's infected at once, you can't tell who infected whom. But what's interesting is that for the complex contagion, we're actually able to recover the network structure at much higher R naught values. This is actually kind of good news. So, just to put this in context for real diseases, so this blue region for this Erdish Rainy network um, on the left hand panel in the last slide, this indicates a region of R naught equals, let's say, 2 to 6. So that actually is very promising for things like SARS-CoV-2, monkeypox, etc. The bad news might be that for things like the flu and for measles, etc., those have R naughts of roughly 10 or more, meaning that for each person that has the measles, they will on average give it to 10 others. Um, yeah, it's not such good news. It means that because there's such saturated dynamics, everyone's infected at once, we won't be able to effectively trace who gave the disease to whom. But on the flip side, this could be actually very promising for things like social trends. So I think I read that for the ice bucket challenge, maybe you remember this. It was, I think, for ALS, and people were pouring buckets of ice on their head and basically saying, share it with a friend. So this is actually quite like a spreading process. And I think someone estimated that it had an R naught value of roughly 2.5. So, meaning that for each person that did the ice bucket challenge, they were able to convince, on average, 2.5 of their friends. So, in this case, it indicates that we might not be able to reconstruct that quite as well as we would hope. But for something that was much more viral, perhaps we could do better. Um, So, some things that I want to leave you with, and maybe some future directions that I'm looking at, are sometimes we actually know what the network is. And so, in that case, maybe we know on Facebook who your friends are. Maybe on Twitter, we know who your followers are. Maybe we've got some proxy of a social network from interviews or just observation. And the question is, can we leverage that to actually create better predictions on less data? Similarly, if we do know the network, maybe we can also figure out how complex contagion is. Maybe epidemiological contagion, maybe it actually has some complex like characteristics in contrast to this simple contagion assumption that I talked about. And lastly, it really comes down to data and the limitations there. So we need to get creative with figuring out how to access data that can help um, make better predictions about who's connected to whom, and maybe how to stop the next misinformation campaign. So with that, I think I will conclude, and thank you for your attention. Yeah.
Yeah, thank you so much, Nicholas. So, thank you for the great slides and also the great explanation. We would now like to inform the audience that we are opening the floor for questions. Please feel free to raise your hand. We will bring you up the stage if you have a question. So, I think there are comments here in the room chat by, yeah, so Jonathan. And I hope that Jonathan can come on stage also to ask the questions to our speaker. So, yeah, I've invited Jonathan to come, and Lisa is also here. So please check, Bob, if they are all here on stage. And anyway, before I turn over the microphone to the audience, I'm just very curious. I would like to ask Nicholas, because in the introduction, I saw that you are also very passionate about open source software, and you founded XGI and hypercontagion software packages to
Yeah.
analyze structure and dynamics of higher order networks. Can you tell us a little more about it? And is this also, progressing as you are progressing in the studies that you have?
Yeah. Great question. Thank you. Yeah, so if you look at the last slide, the network visualizations were actually done with XGI. Um, yeah, there's actually quite a robust community surrounding XGI. Um, it turns out that if you do the same thing enough times, you get sick of copying your code and doing it wrong. So you create a package and hopefully other people can use it. Yeah, I'm super excited about XGI. It's actually more catered to higher order networks. I mentioned briefly that maybe two people connecting at once might not be a great assumption. And so higher order networks basically break down that assumption and generalize it and say that groups of people can interact at once. So that's what XGI is for.
Uh, is this is this open? Yeah, you said this is open. So how can people access it? Or is there a site
Yeah, I will.
to go to?
I'm putting it in the chat. Hopefully it works.
Yeah, I think it's very important because if it's open and I think people can really use it.
Yeah,
Even me, I'm very interested in that because of a lot of applications.
yeah.
And of course, I know that you were also doing some work in the Complex Systems Institute. So, very, very interesting for this study. Anyway, I have questions later if there's time for me.
Yeah,
But
definitely.
there are a lot of people who I think would like to ask you questions. So,
Yeah,
uh, questions on the room chat, and we have Jonathan. I will announce in PTR order. Please correct me if my order is wrong, Bob. I have Jonathan, Lisa, Node, and Kevin on stage. So, is this a correct PTR order? All right. So then I will give my mic to Jonathan. Go ahead, please.
Oh, thank you, Cecile. Nicholas, this is great research. Thank you so much for sharing.
thanks.
Um, so I would assume that some of the best data sets for your further research would be the social network sites. Um, have you been able to talk to people at Facebook or TikTok or whoever?
Yeah, great question. So it turns out that data is always the challenge, um, especially with a lot of people in my community were using Twitter before all that happened. So they actually signed up for people at the Vermont Complex Systems Center, now Institute,
Mm.
signed up for what's known as the DECA hose. Have you heard of
Uh-huh.
that?
Yeah, yeah, yeah.
So, yeah, but unfortunately, there's lots of like legal trouble with that. So there are limitations to getting this data. I know that people have been looking into things like Blue Sky and their API for
Oh,
getting this,
nice.
but that's still kind of gaining popularity. It's not quite as established as Twitter was in its heyday. Um, yeah, so actually, what it's interesting you bring this up because this came out of what I would call a failure of a project, where we basically we got a bunch of electronic health records, which is actually kind of a fascinating data set.
Huh.
We wanted to predict how C. diff was going to spread in the hospital and try to figure out how it was spreading.
I'm sorry. How what would spread?
Oh, sorry, C. diff. C. difficile. It's this really, really nasty hospital acquired infection.
Oh.
Yeah, and so that we've got a ton of data on that, and basically, electronic health records encompass lab tests, and it covers which doctors are in contact with which patients, and where the patients were moved in the hospital, and what drugs were they given. And the idea is we can kind of construct this complete picture, and a lot of people more well it's actually not true. More so in recent years, there have been people looking at the network structure, but a lot of people just focus on the demography and say things like if you've got antibiotics, if you're older, etc., then you're more at risk. But there's also some serious network considerations. Like obviously, if someone has C. diff and you're moved into their room and they're asymptomatic, you are much more at risk.
Okay, a more meta question. To what degree is epidemiological contagion truly analogous to thought contagion?
Great question. I think if you talk to the social scientists, they'd say not very. Um, yeah, so I went to this fascinating talk by one of my collaborators, Jimmy Adams. I think he's now at the University of South Carolina. And he has this idea where the way we think affects our behaviors, and our behaviors are homophilous, meaning that they
Mm,
attract similar, and then those in turn affect the way we think. Um, yeah, it's an interesting question. We kind of throw around the term contagion, but you're right. I think we need to be a bit more careful.
yeah, so homophily doesn't seem to necessarily map onto um, epidemiological and thought contagions.
In what sense? Oh, are you there?
Yeah,
I was saying in what
did you
sense?
hear my question?
Yep, I said in what sense.
Um, I just have an intuition that they don't map.
Yeah. Um, so in the social science literature, it's known that people with like similar risk behaviors, there is some homophily there. So classic example being like smoking. Um, as far as contagion goes, uh, people, I mean, right. So social mixing, at least when we're talking about contagion modeling in the epidemiological sense,
Mhm.
a lot of people, when they want to take one step away from true networks, they do what's known as age mixing models, where you basically look at how people of different age brackets mix with one another. And the basic idea is that it is homophilous. Um,
Mm,
and so we can basically treat the behavior in each of these age compartments similarly.
cool. I also want to send you a link to research of a very dear friend, Tim Clancy,
Oh,
who is
awesome.
very interested in this kind of stuff. So should I just post it in the thread here?
Yeah, that'd be great.
Cool. Thank you.
Does this persist over time?
Yes.
Okay, perfect. Thanks for the questions. Feel like they're really thought provoking.
Yeah, so I also had a question, and I'm curious about higher order dynamics. Like, if I have a whole population of gut microbiome things, and you mentioned C. diff, like, are you expecting to be able to predict different, like almost analogous to the neighborhood pattern or the age mixing pattern, where we might be able to deduce specific populations that are correlated to particular diseases and give you a fuller picture of sort of the symptomatic versus asymptomatic spread and this sort of thing?
Um, hmm. Let me see if I understand. Where does higher order play in this?
Well, I'm just thinking that your bacterial community, like your gut, is in itself a community and has some level of contagion.
Mm,
So there's both the exposure to an illness or something, but then also
yeah.
whoever, yeah.
Okay. So are you almost talking about there's like different scales at play. There's the like full ecological network, but then like within hosts. Uh
Yes.
that's so interesting. I know that there is work. I'm not so much involved in it. I've seen work on higher order stuff looking at the metabolic dynamics of different bacteria. The idea being that you want to like starve different pathways to weaken the bacteria. But that's not so much my work. But yeah, it's something I've wanted to get into. But maybe, I don't know, could you rephrase your question so I can answer it more effectively?
Yeah, so if we look at it from the other domain of social networks, this would be something akin to mediating ideas or pathways that lead one toward a specific group or this sort of thing. Like you would be able to, I guess, trace with more detail externalities to your graph that would,
Yeah.
yeah.
Yeah. I mean, here's what I'm so excited about. I think there's so much you can do with this approach. So I think there was this famous paper by Damon Centola where he basically set up this online experiment and basically said that contagion, at least when we think about it in the social setting, is complex. And that's kind of the reference that people are usually thinking about when they think about complex contagion. But as you kind of alluded to, it's maybe a bit more subtle. And so things that I'm thinking about are, for instance, it's not so simple when we're talking about social media, at least in its modern iteration, because a huge factor is the algorithm itself. So we've got this almost artificial community that we're getting served to us. So if you look at Facebook, for example, I'm like afraid to look sometimes, but basically, if I think I counted one time, it's roughly half ads, if not more. And then there's also half of my actual friends. And so the idea is, can we kind of disentangle these effects? Um, how might we expect, these ads uh, to affect our opinions? And then can we differentiate them from our real friends? And how do each affect how we change our opinions? I'm not sure if that actually answered your question, but that's my
Yeah.
attempt.
No, thank you. That was it exactly.
Yeah, thank you, Lisa. So here in PTR order, we have Node. Node, are you able to speak now?
Yes, I was just sending a back channel to Nicholas. I find this highly interesting. I'm doing a program in machine learning, so there is a network science and time series course, and I always wanted to
Cool.
know. I doubt that it's going to be this interesting, but uh, yeah, I'm definitely gonna have to read this paper later. I'm actually with UC Berkeley right now, and they're doing this carbon nanotubule thing for disease detection. So they had this like lab on a chip thing before,
Hmm,
and I don't
cool.
know if this library you have can be used, but I'll definitely look into all of this. Yeah, it's
That's
interesting.
awesome. Yeah, I'd be curious to know what they're teaching in that. You said it was network science and time series or machine learning and time
Yeah,
series?
yeah, it's with the Georgia Tech program for
Huh.
yeah. UC
I
Berkeley
should
has one
look.
too. Stanford has one too. But that's customary. That's like one of their classes, network science.
Wow. I'll have to look into that. Thanks. Yeah,
Yeah,
I'm
thank.
always pitching XGI. Highly encourage you to use it. I think, so it's been in existence for 3 years, and we actually merged two libraries to make it. So it's like the brainchild of, I think, 8 or 9 researchers in higher order network science, and actually like pretty well known higher order network science researchers as well. We poured a ton of time into it. So if you use it and it doesn't have all the functionality you want, or you're going through some of the tutorials and get stuck, feel free to reach out.
Yeah, thank you, Nicholas. Kevin is here, and we'd like to give the mic to Kevin now.
Hey, Nicholas, I just want to make sure that you know I can tell that you're not on Clubhouse much. I just want to make
No.
sure that you saw the link I sent to Tim Clancy.
Okay. Is that in the chat?
Yes.
Yep, I see it.
Great.
Awesome. Thank
The
you.
guy's
Yeah. Sorry.
the guy is freaking brilliant. Absolutely brilliant.
Okay. Thanks. I will make a note of it.
Yes, so I'd like to give the mic to Kevin now.
Oh yeah, thanks. Yeah, this is very interesting so far. But some of the most important questions I can think of. I mean, I think it can go on for a while, but
Mm.
just some simple ones, maybe like how does your method, handle noisy or incomplete contagion data, and what about scaling things up? And if you could
Yeah.
compare your approach to existing network reconstruction methods, is what I can think of.
Yeah. Wow. You got to the skeletons in my closet, I guess. um,
Oh,
yeah.
sorry, man. So,
No. These are like
oh,
really great questions. So, and there's things I'm thinking about. So, I'd like to go on my soapbox for just a sec on Bayesian inference. I really love it because you have to specify your model. You have to specify the way in which you think the uncertainty shows up. And so right now, we assume that we have perfect information. It might be noisy information, but we have complete information. So when we talk about missingness, like you're suggesting, which is, how the real world works, even in this EHR data set, because it's real data, we've got, missing patients. Don't worry, they're not actually missing. It's just their records are in slightly different formats. And of course, it makes our life harder. Um, so yeah, the question is how to incorporate missingness. So basically, you can create hidden states for states you don't observe, and you can kind of integrate all overall possible states that might be there. Um, you can try to impute them. I know that people in the electronic health record space try to fill in missing rows based on what they know from the other entries. Um, So that's kind of to answer your missingness question. The other question is efficiency. And yeah, this is a pretty expensive process. Something I want to comment is that in the case when you know the network perfectly, let's suppose that I actually know, someone at Meta or X gave me the keys and I was able to access the entire social network. I would actually already have that network, and then what I could do is actually just perfectly infer or reconstruct the dynamical rules of how that contagion is spreading. So there's still some exciting possibilities there. But to answer your question, it is very expensive. And the reason why it's expensive is because a lot of times people do like an expectation maximization algorithm where what I showed you was the full distribution of networks, like just sampling from that distribution, but a more, let's say, computationally efficient way would just be let's look greedily for the most likely network. And so that's one way around it.
oh, okay. Yeah. Then maybe the other thing I can think of is how might these reconstructed networks inform our understanding of systemic resilience, competence is the other
Hmm.
one I can think of, maybe.
Yeah. Um, I'm trying to think. I don't work much in the space of resilience. I know that a lot of researchers work on like network robustness. Are you talking about things akin to cascading failures and such?
Yeah, that's from what I've heard before. Yes, exactly.
Yeah, so that's a really interesting topic. Um, and I don't work much in that space. What I can tell you that I'm kind of excited about is I'm trying to work on inferential methods for some other real data sets where the network is quite important, and we need to identify these critical hubs that may fail. I've been recently collaborating with some researchers. Um, working on trying to infer the mobility networks. So basically, a mobility network is, instead of people being nodes, now locations are nodes. And then a link between two locations means that people travel between the places. And then, of course, the weights on those links are how many people, or the volume of people that travel between those two places, maybe within a given time. And so we can think that, in remote or third world countries, if there's, say, a rainy season, the topology of that network can change quite dramatically. And so, what I'm working on right now is trying to reconstruct the mobility network in Guyana, in this particular region, to try to more effectively treat malaria. Because if you can figure out where people are flowing and you know who's gotten sick, you can more effectively screen and treat. And I know I totally sidestepped your resilience question. I think it's an interesting question. I don't think I'm the right person to answer it, though.
Yeah, thank you, Nicholas. Well, I think in order to address resilience, you need data actually, because your analysis would also depend upon data. I would just like to share this because I have a friend who is using satellite mapping in order to help some people in climate change. How is it affecting their crops, and yeah, so also some people will have some kind of resilience in, I think it's in Africa, so in
Cool.
terms of their farming. So but of course you are dependent on the data that's provided. So yeah, I think these
Mm,
tools are also very important.
totally.
Yes, so there's a question at the room chat from Shane, and I invited Shane to the stage, but maybe he could not speak now, so I'll just read it. And anyway, welcome, Shane. Long time no see. So Shane's question is: were urban planners able to assist in the research?
Hmm. I'm not sure I understand the question totally. Um, the short answer
Shane,
is no. Yeah.
Shane is here. Hi,
Hi.
Shane.
Hello. Um,
Hi,
so,
Shane.
hi. Hello. A great research. Very interesting. Your graphic of the folks crossing the interstate is what really inspired that question. And
Mm.
so, I have an urban planning background, and we do various things like that. And so, I was curious
Hmm. That's really cool.
them to just like throw
Yeah.
ideas off of one another.
It's really interesting. I'm thinking of, I saw a paper and I can't remember where, but basically treating people like fluids, and basically observing how people walk around obstacles and such, and just noticing how people flow in crowded spaces. Um, yeah, I've thought about this, and something that is kind of interesting that comes up for me, and I know this is not at all what you're asking, but I just want to share it, is that, like, what is a connection? What is a group? So when I'm thinking about this sidewalk example, we kind of have some
Great
proxy.
point.
What?
Those are great points, and like very serious questions.
Yeah. Um, so,
Nodes are is like a way or like to like describe an area, but if you're looking at from like bird eye or plan view, like the connection elements, those connection points, or I don't know. I think nodes is what I
mhm,
attach to the most. Um,
yeah,
like yeah, like how do those work?
like when you say how do they work, like, are you almost asking, like, how do I choose what they are,
Well,
essentially?
I would say as an observer, like I would say so. Just like watching, so developing your graph, it
Yeah,
depicted something over time, and
yeah,
then you're able to identify like hot spots, and then
yeah.
you can ask the question like, why are those spots hot?
Yes.
And that's just kind of like the, I guess maybe rhetorical or open ended like thought I
Yeah,
have.
yeah. Um, yeah, that brings up a lot for me. Really interesting question. Um, yeah, so there's so many ways to represent a network. There's so many ways to choose nodes and links, and what we observe as being hotspots or whatever will depend on those choices that we make. So going back to your uh, aside about urban planning, so sometimes people look at the networks of cities, and in those cases, we have, I think it's sometimes that road intersections are nodes, and then roads themselves are links. And when we're talking about hotspots, for example, we're looking at intersections that are visited by a lot of cars, for example, or maybe they're bike paths. If we're looking, so a lot of people use co-location as kind of a proxy for connection. So I think back in the day, it was Foursquare where you would check into locations. I actually have a data set that I worked on with that. And so you can get some proxy. So that's kind of an interesting thing. We're getting rid of a layer of complexity when we look at just a pairwise network like co-location in a sense, because if I look at an area, let's suppose I create, I don't know what they call them, like a geofence or something around some area, and I just
Yep,
observe
yes, yep.
who walks in and out of an area. So if people are in that same area simultaneously, I could call them connected. But like it really depends on the size of that area. It depends what time scale I'm looking at. And going back to the Foursquare example, this may be over uh, different times. It could be months, it could be days. And so it may not be that they're connected. It's really that they're connected to that location. And so in that case, that location might be a hotspot if many people are visiting it.
Okay, I mean that is a beautiful and great. Uh, I love your response to the answer or the question. Uh, but yeah, and so I mean, I would say the only thing that might be is integrating maybe not infrastructure, just like built environment elements to the general dispersion of hotspots that might tell more
Mm,
about why it makes sense that those are where they are. And I think we'll probably determine like intersections and whatnot and so forth, but uh, might depict how or why they're interacting. Like, are they seeing it as in my mind, I'm thinking back to COVID because maybe
yeah.
that's most relatable. Like, are they all standing at a stoplight in a close proximity, or are they like getting coffee and board in line and like exchanging conversation?
Mm,
But also, like, those would be interesting things to see if you could see in. Uh, by the way, I love your graphics. I think they're absolutely fabulous.
thanks.
So that's really cool.
Yeah. It's really interesting to bounce off of what you're saying. So I think a lot of data that people were getting during the pandemic is from your cell phone. And there's some like ethical things that go along with that. But yeah, it's really amazing the types of or the amount of resolution you can get from that. In fact, I am loosely affiliated with a institute at the University of Virginia. It's called the Biocomplexity Institute, and I'm sure people have heard about like digital twins. So they work a lot in that space, um, where they literally have like down to the street and house level, maps, and basically they're using that kind of data that you're talking about, where they're like actually observing people's commutes, and then they're basically creating risk profiles for different counties and such. And they've actually done this on the US level, which is wild.
Yeah.
Uh,
Go ahead,
I
Shay.
really hope you continue this research with all the continuing questions you might have. I like. I'm very intrigued, and I hope there's more advancement.
Thanks so much. I really appreciated the questions.
Yeah, thank you, Shane, and thank you, Nicholas. So, Nicholas, you mentioned a while ago about fluid dynamics, and I think it's very interesting, but I think you did not finish the actual point that you wanted to make. Would you like to continue talking about it? Because that's what also got me so interested in complexity science. So, but in relation to what your research is now and what you mentioned earlier, can you please tell us a little more about what you were going to say a while ago?
Yeah, you're talking about when I was mentioning the sidewalk, like, and people going around obstacles kind of thing. Yeah.
Yes.
Yeah. So fun fact, I was actually an engineer in my first life. So basically, my undergrad was in mechanical engineering, and I actually did research in fluid dynamics um, until I decided to switch to applied math. And yeah, so I'm certainly not saying that this is, something that will hold up under scrutiny, but I've often thought about people can be thought of as kind of coarse-grained fluids, in my opinion, when they're walking down sidewalks, because and even cars. We notice, like on the highways, for instance, there's the development of traffic waves you can easily see where people will stop, and because of the delayed reaction and the feedback loop there, you actually get like a traveling wave like you might see in a fluid. So, kind of my comment was just talking about these large agent systems like people or cars exhibiting, qualitatively, let's say, similar behaviors as to what one might observe in a fluid. Like, for instance, well, and so I don't know if that analogy really holds up under scrutiny, but it was just something I was thinking about.
Yeah, I think it's very important for, design systems and also designing architectures for crowd control, also for
Hmm.
design and risk management. So that's why I was, how do I relate it also to networks? I was just thinking, it's just an intuition
I've noticed in
came up.
urban. Oh, I might be in the matrix. Sorry,
Shane, were
Sorry.
you speaking?
I don't know if my audio is coming through.
Oh, okay.
Oh,
Yeah, so
matrix means like lost in like lag time.
sorry, I couldn't hear you, Shane.
So
Yeah,
on the
Lisa?
yeah, just on the fluid dynamics, I know that they have used that approach for mapping bird flocks and fish schooling, like the flock behavior. And if you set like some minimum rules, apparently it's a pretty close approximation.
That's cool. I did not know that. Huh. Um, I will say something really briefly is that I think, yeah, the most akin to fluids or waves on networks is looking at traffic flows and treating those. Yeah, there's got to be some kind of conservation between points because you can't just spontaneously disintegrate cars or add them. So you need to have conservation.
Yeah,
But yeah,
thank
that's
you.
cool. Oh, sorry.
It's okay. Yeah. Thank you, Lisa and Nicholas. And I've got a question here that was sent to me by Randall. His
Mhm.
question is: in light of your research on how both diseases and ideas spread, do you think that the dynamics of social contagion, such as spread of misinformation, pose a greater long term threat to society than the spread of physical diseases like COVID 19? If
Oof.
so, how should we prioritize our efforts to address these two types of contagions?
Wow. Yeah, that's a that's a hard question to answer. Um, so it's really interesting. A lot of researchers, so there's more than one type of network. And so there's networks, right. And so simultaneously, we're part of many of them. So you've got your social network, you've got your work network, etc. You've got, online friends, etc. And there's different modalities by which epidemiological transmission will happen than social contagion. So I'm actually currently working on a project looking at how the two inform one another. So, like, people have studied how do we vaccinate people if I've got a limited budget of vaccines and I want to optimally control uh, an epidemic. The question then becomes, though, let's suppose I can convince people into, say, getting those vaccines or wearing a mask, for example. Um, yeah, like how do those two things interact with one another? So there's this paper by Damon Santola. I need to pull up the paper, but it's really cool. So there's this concept in network science called centrality. A common one might be eigenvector centrality. The basic idea is the more friends you're connected to, or the more connections you have, broadly speaking, depends on, or it will affect how you spread. So, like, the more connections you have, the more you'll spread. And there's this paper. It's called topological. I'll have to find this after. But basically, they show that for complex contagion, it is totally counterintuitive. So, for simple contagion, you basically want to vaccinate the hubs and break the network apart and focus on the highly connected individuals. And vice versa, if you want to spread a contagion, you start there as well. But let's suppose that you want to convince people to adopt a trend or to believe a certain thing. Counterintuitively, you do not want to start at the center of the network. Again, Damon Santola is at a talk last week by him, and he was mentioning that people who are in central positions of power sometimes are there because they've gotten there and they have a lot of pressure on them to like maintain that image, whereas people on the fringes are more flexible to adaptation and to adopting these opinions. And so we actually notice when we think about social contagion, maybe misinformation or information, it'll spread around the edges until it reaches some kind of critical mass, and then it'll sweep through the whole network. And that's really, really interesting when we think about, okay, I think I might be sidestepping your question. I think you asked, like, which is more harmful? I think they're both really important. And we address these in different ways. I think the question itself is more of a philosophical question because, like, how do you quantify harm? Obviously, there's harm through death, through long term illness or illness. But with misinformation, like, it's really hard to quantify like harm in that sense. It's obvious that there is, but how do we measure that? And so for that reason, I'm not sure I can give you a good answer on that.
Yeah, thank you so much. It's actually a great answer. So I'm just reminded when you said that, if you have to work around the edges in order to influence the middle in all old times, of course in communism, that's what they are thinking about philosophically, and in trying to make strategies you surround the countryside. You go at the edges until the
Yeah.
center could not resist anymore. So yeah, I think it's a great answer because people have to, deliberate about it, and how you are able to put this to pragmatic and also ethical use. I think it's very important. So I would like to encourage you to continue on your studies. And also, by the way, Nicholas, I would like to share with you that Dr. Sentula was our guest speaker sometime on October, also on 2022, here in
Oh,
Quantum.
really?
Yeah,
That's awesome.
his topic was change how to make big things happen. So I don't know, since the time I haven't seen recent papers from Damon. So, but of course, he was invited here because of my interest in network science and complexity. So, yeah, I think it's very awesome also to talk to you, and sharing updates on your own work here. And
Thanks.
anyway, there is a question maybe here on uh, the room chat. And however, I will first ask this question. This is a follow up question as asked earlier. Um, by Randall. He said, as our ability to track and model spread of both diseases and ideas improve, do you think there's a risk of these insights being misused? Of course, you know where this is going. This is more of an ethical question, but actually it could happen. So, as manipulating public opinion or controlling the narrative in social networks, how do we balance the benefits of understanding contagion with the ethical implications of its application?
Ooh,
Yeah, we could
this
also see
this
in
is such a
Twitter how algorithms and exposure are being manipulated in addition to fake news, actually, in order to swing people to vote, for example, for a certain candidate, and how tricks about marketing are also being manipulated to get people to act. So anyway, yeah, I
yeah.
think it's some ethical, and yeah, we should talk more about it, because of course in every kind of science or advancement in knowledge there is always the ethical question. So
Mm,
but anyway, can you speak a little about it?
yeah. Yeah, thanks for the question. I'm thinking about I saw this really great talk 2 weeks ago by Josh Garland. He runs the Center, let's see, for Narrative and Misinformation. I'm mashing up some words together. I think it's got narrative. Anyway, it's at ASU. And he gave this really, really fascinating talk about how do we combat misinformation. So, like, this gets back to like bad actors. You know, we understand more about contagion. We understand how to efficiently seed the network and like plant people in and have them spread, you know, a certain idea or something. So if we know how to efficiently do that, you know, we need to obviously combat it. And I think it's this kind of Josh Garland called it information warfare in a sense. I mean, I think that's unfortunately what it can turn into, where people understand that news, like, so as humans, we are just deluged with information every day. You know, through social media, if we're scrolling, or all the news that we see, or the ads that are in everything. We've just got so much information that we're processing. And so that's like the perfect avenue um, by which misinformation travels, I think. That we actually need to slow down and take space and think about what we've read and not just swallow it hook, line, and sinker. That we actually think about it. And that's really challenging to do with the information saturation that's going on. So I think that is just, I don't know if there's a downside to that. But I will say, so going to the actual question, um, where it's like, how do we balance knowing more about contagion and then, yeah, I don't know how you can get around that because, um, yeah, that's a really tough question. I think I'm committed to continuing to understand all this and hope that it gets into the right hands, and at least we'll understand it better, and then hopefully that will incentive or it will streamline the fighting it as well if there's bad actors.
Yeah, I think, you know, at this time we're just trying to transpose what's really there in the data in a study. But this kind of contagion has been existing since immemorial, and we're just trying to analyze what's happening actually, because we can at this point in time. So, but it's good to do this analysis, because depending on how we try to use it, I must admit that we could put it to good or bad use, whichever way we try to turn. So, but yeah, I think it's
Hmm.
important to continue on discussing the ethics of this, just like any kind of technology that we have. So,
Yeah,
uh,
totally.
there
Right.
are.
Well, it's so.
Question?
Oh, sorry.
Go ahead, please,
I just want
Nicola.
to really quick follow up. So, um, in this talk that I was mentioning, they were basically trying to train some kind of bot to detect fake news because we've all seen fake news, and it's one of these kind of arms races where to your point, yeah, you get better detection of fake news, then they learn, and then they get better. It's escalating. And it's actually pretty hard to detect fake news. I took a quiz and I did pretty poorly.
I think now when you look at studies in AI,
Hmm.
some of the studies that have been there for like, yeah, this year actually are looking at also how to combat fake news, and at the same time how to do watermarks on LLMs generated response
Hmm.
like a chat GPT. So yeah, there's always something that we study, and like even in trying to do some hacking, in systems, it you try to make a solution, and then the next hacker gets better and better, and you just need to continue on giving solutions. So yeah, I
Hmm.
think that's the issue. So yeah, we have questions here on the room chat. There is a question from OV and also Chavis Richan. So I will ask the question of OB first because there's only one. And OV is asking, can we model lifestyle disease like diabetes based on behavioral patterns using this? And if so, how?
Yeah, that's a great question. This is a little bit outside of the work that I do. But again, so I have uh, a collaborator, Jimmy Adams, at University of South Carolina. He's much more adjacent to this type of thing. And yeah, there's a lot of cool work in this space. I'm trying to think what the model he used uh, particularly for this was. I think it is Sienna, maybe. Um, it's some fancy acronym. But yeah, there are people thinking about this. To answer your question, can we use this? I think we could. The problem is the model certainly would need to get tweaked. I don't think that's an effective model or very descriptive of what's actually occurring in the system that you described.
Yeah, thank you. So Lisa also posted some, maybe you can see this later. Lisa posted some link here about flow interactions,
Oh,
which,
cool. Yeah, I do
yeah,
see that.
yeah, you can see
Thanks,
it
Lisa.
later when you check the replay. And
Yep.
there is Chavez who has been saying adjacency matrix could be hallucinated similar to attention in LLM. Apart
Hmm.
from that, is chaotic system for nonlinear systems like fluid dynamics would lead to chaotic spread of the messages through the network, butterfly effect in the network. Chavis, can you please clarify your question about this so that
Yeah, that would
so
be best,
that
I think.
I'll bring Chavis here up on stage. But Chavis, yeah, please remember, always give space to some other speakers, and please don't hug the mic. Thank you. Okay, mic to you, Chavis. Now, please clarify your question.
Hi, Cecile and Nicholas. So I think you are expert in fluid dynamics. You know, the equation is nonlinear, right?
Yeah.
So Navier-Stokes equation. So I think the same thing happened to the social medias and the networks because some news it gets spread like like butterfly effect. I think it's just the idea that sometimes right now we use graph convolutional neural network to model the weather forecast for the whole world instead of using the Navier-Stokes equation. So
Hmm.
I think it is pretty interesting because what you say is that yeah, you try to model the social networks and the fake news using yeah, I think your intuitive maybe in fluid dynamics. So I think it's the same thing. Maybe if we can detect if the network is already in chaotic conditions,
Hmm.
and then then the news that you put and the message and you put into your network will be, I think definitely there will be some butterfly effect. So I'm so sorry I came here late.
No worries.
But I read, yeah, but I read it. Yeah, but I think yeah, you have different types of network, and you say some some types they prefer more spreading of stuff. So I think, yeah, I think if you know fluid dynamics, the same thing. Yeah, if you know nonlinear system and chaotic system, it will be the same. So
Yeah.
even a little a
Yeah.
little bit of
Yeah.
initial condition change, and it will lead
Right.
to different change. So it is butterfly
Yeah.
effect, I would say. Yeah, maybe
Um,
we can do something together about this, because I got bad news, sometime. No, no, until now
yeah.
in social
Yeah.
network. Yeah.
Yeah. Thanks for the question. So I wanted to talk about the butterfly effect that you were mentioning. And so there's actually a paper that I have in mind, and this really lives in my memory because it was written by Sam Scarpino and Giovanni Petri. And this is actually, I think, when Sam Scarpino was actually at UVM. And there's this infamous sandwich shop called Four Corners of the Earth, and it's just a gem. And they wrote this paper in that sandwich shop, and they dedicated uh, they either dedicated or acknowledged the paper to the sandwich shop owner, which I thought was kind of fun. Anyway, this does answer your question, I promise. And what they showed is that that's exactly what you see. There's this butterfly effect. There's this fundamental limit to the forecasts that you can make into the future just because of those effects that you see. We've got these stochastic processes, so you can only forecast out so far, and that's true not only in these fluid dynamic systems, but also in these nonlinear contagion type dynamics.
Oh, thank you. That's great, Chris. Great answer. Yeah.
Yeah, so this is a joke, Nicholas. This is not quite the butterfly effect, but talking about, some ideas which are placed on the napkin was the start of NVIDIA before, because I think the founders tried to write something in a napkin, and then there came NVIDIA now.
That's awesome. Wow.
Yeah, so yeah. So I was just thinking about it, and also about the butterfly effect in relation to the spread of, networks in the study that you have. So I was also thinking about that, but probably there is some more deeper insinuation maybe that we can discuss in the future.
Yeah.
So there is there is Kevin. Kevin, did you send me a message that you would like to speak a little bit?
Oh no, not actually. No, the only thing I could think of right now is, and this has been very thorough, and I love it. But is well, I'm eating right now. Sorry. Is marketing. How do you think this for marketing applications might be used? Sorry.
Yeah. That's a amazing question. Um, so it kind of maps to a problem in network science. Full disclaimer that this isn't my area of expertise specifically, but it is in my lab that I was part of at UVM. And the problem is known as influence maximization. The idea is for a certain budget, you know, I mean, if we had unlimited ad dollars, we could just uh, blast everyone with the same information ad nauseum. But we have a limited ad budget, so that constrains who will see our message. And then the question is, how can I most effectively distribute that message to influence the most people? Um, so yeah, when we think about like how to place ads, I think the way I would do it is I would say, okay, let's go out into the field and let's see how people react to, you know, their friends sharing, maybe different products. I guess we're hoping that they spend money, um, it being an ad and all, or maybe it's like voting a certain way or something. And then basically, I would see how they reacted based on what their friends were doing, get some kind of sample so that I could determine whether the contagion was simple or complex or something in between. And then what I would do is I would use that and I would basically map that to some kind of centrality, telling me who is the most influential in spreading this. And then I basically would just randomly distribute the message amongst those people I determined were most influential.
Yeah, thank you. Yeah, so Nicholas, I would just like to mention that maybe ex post facto after the elections in the United States, it would be
Mm.
very interesting to look at Twitter data on how it was used. Whoever wins, it's very important to look
Yeah.
at maybe how this social network was manipulated. As you see, a lot of our friends who are scientists have
Yeah.
left Twitter already and had gone
Yes.
to Blue Sky. And
Yeah.
however, you see how the algorithm is being manipulated and the kind of fake news and also the true news that people who are campaigning, like on the part of Elon Musk and also on the part of the Liberal Party, how
Yeah.
is it being used in order to sway or influence behavior? So, because of course, in the past, our social media is not as well connected as what we have now because there are more people in the world who are in the internet, in the social media platforms, as compared to, the past, even if we had the internet. So I thought that maybe whoever wins in the election, it would be very interesting to look at how, the network social contagion happened and what kind of
Mm.
are they using.
Yeah.
I have a
Yeah.
question. I have a question.
Yeah.
When I started my program, I know it's not really relevant, but we had this course where we were doing data mining and like point of interest type of node data mining. And then
Hmm.
what I'm wondering is, well, since I'm pretty familiar with like procedural programming, subroutines, stuff for microcontrollers, but like machine learning and writing a library. Uh, Hopefully, my signal isn't going bad. Like writing a library, I don't know how you did that and how difficult that is, or how what your opinion of coding, like machine learning coding and all that kind of stuff is. Would you be able to elaborate a little bit more on that and how you wrote an entire library? Because it's personally, I don't have as much familiarity with it, and it's still a little intimidating for me. But I don't
Yeah.
know what it's like.
Well, if you think it's intimidating, you should look at phase one, which definitely does not look like it looks like right now. So it's been 3 years, and it's been contributed to by a bunch of people. So certainly not been a solo effort. I think what I would say, which is less technical in mind, but I think having good mentors in the coding space is really important. And it's actually pretty lucky that there's some really great folks. Just off the top of my head, there's an organization called Pi Open Sci. I'll type it in the chat. They basically, if you come up with a software package, they, like free of charge, will review it for you and basically bring to your attention any like deficits and whatnot and walk you through it. I will say that there's a great community in network science where people are helping each other with coding and getting things off the ground. For me personally, I started XGI, for instance, with a guy named Leo Torres. He's since left academia, and he's a data scientist in industry. But there's a lot of just like unwritten rules and things you just have to learn the hard way when building a software library from scratch. And I think the biggest thing is the processes. I think a lot of people have the ability to uh, write code. What really becomes challenging is managing a big code base and doing it amongst many people. So you have to kind of learn best
So I
practices.
looked at this.
Oh, sorry.
Sorry to interrupt. I was watching if my voice is coming through before my signal goes bad again. I
Oh,
was
yeah.
watching this video the other day, and they had this cross comparison of, say, Google Chrome has 40 million lines of code.
Yeah.
I don't know, like a game has, say, a million, and then whatever else, some basic
Yeah.
like software has 10,000. Like I don't even know how they manage those million line code type of projects,
Yeah.
uh,
Yeah. Fair enough.
or these communities. So I'm not the type of person who would go on code wars and do all of those different exercises. And frankly, I find my program a little bit uh some of the courses in it a little useless. And I don't know, my mentor has been around since homebrew, and he's looked over some of the stuff I have, and I don't know what like actual machine learning code. Well, it kind of varies, I guess. If you're in industry, it varies versus if you're in academia.
Yeah.
um,
It's
and
true.
it's overwhelming. It's like a huge space. So if you have
Yeah.
any other communities, I'll join or look into them.
Yeah. So I find that a lot of I don't know if you've heard this suggestion before, but a lot of um, developers at some of these open source projects, let's say NumPy or SciPy, like I'm in on some of these meetings, so I'm aware that there's just like, they're wearing too many hats. And so basically the practical suggestion from all of this is people will not usually say no to contributions. And so sometimes a good way to start is to repositories will have like good first issue, and that would just like get your foot in the door. Look at that issue, see if it's something you could conceivably address. Maybe start with like a smaller library. And then once you get your feet wet, you can decide whether you want to do it.
Nicholas, are you still speaking?
Yeah, I just
Ah, I
abruptly
thought
ended my thought.
I thought we lost you because sometimes there's a glitch. So
Oh
yeah,
yeah.
thank you so much, Nicholas. I know that we've been here for 1 hour and 30 minutes, but I neglected to see Ovi, and thanks Kevin for reminding me because Ovi hasn't spoken yet. So Ovi, if you'd like to speak, we'd like to give the mic to you.
Yeah, Nicholas, so my question was whether this kind of libraries can be used to recognize patterns in the behavioral diseases or occupational diseases. And for example, we know the certain kind of patterns in the behavior make the probability of person getting diabetes greater. But um, can we model behavior of masses in terms of probability? How if they do this thing, they have the larger chances to get some kind of disease, and then tweak some linguistic models on top of that or something like that to tweak those behavioral patterns. Is there any research done for the masses?
Okay, so you're asking about a model for what? Sorry, you cut out.
For detecting the behavioral patterns that will
Yeah.
like uh, tell you that the probability of getting certain kind of diseases more if they do certain kind of things. And
Mm,
second question is there are some modalities like neurolinguistic programming or behavioral things that could be modeled in terms of mathematical models. If is it is a possible, then can it be used for tweaking the behavior and preventing diseases on the larger scale?
Yeah, thanks for the question.
And any
Go ahead. Sorry,
yeah,
were you going
so
to
I
finish?
wanted to know if any research going on around this idea.
Yeah. Okay. I hope I can answer your question in the way that you intended it. Something that I'm thinking about is so there's this notion of group size. So, like during the pandemic, for example, at least in the state that I was living in at that time, I was living in Colorado when the pandemic happened. And so basically, there was guidelines surrounding the size of groups that you could be in. That there were different risks to uh, being part of groups of different sizes. And so, actually, one of my mentors at University of Vermont created a nice little mathematical model showing that contagion tends to localize in the largest of groups. So it actually can be pretty effective to limit the group size if you want to contain uh, a pandemic. Um, yeah, so I think that was me responding to your comments about risk behaviors. As far as different diseases, there's a guy, Josh Whites. I think he just moved to University of Maryland, and he was involved with. I don't know if anyone saw this risk calculator during COVID. Basically, you plug in all these data points as far as like I'm planning on doing this. Um, this is the size of the group. This is the environment, and then it would output some kind of probability that you would get sick. And um, yeah, so I think those are my initial thoughts. Maybe let me know if you want me to go in a different direction on this question, and I might have misunderstood.
Yeah, we are talking on the same page. I just wanted to know what the things are going on around and how I can
Yeah.
access those. Thank you.
You know what's really interesting though? So it turns out that people um, overestimate their risk, so they think it's more risky than it actually is to hang out in smaller groups, and they underestimate how risky it is to be in larger groups. So there's this kind of interesting thing going on, like psychologically, where we don't accurately assess like the risk of certain behaviors. I think that's kind of an interesting area of research in the future, where we kind of model how. So we've been talking about, how behaviors spread, how can diseases spread, but it's also like how we perceive it is so important too. Um, yeah, because there's this interplay between my awareness about diseases, for example, or my awareness about misinformation campaigns, and like how risky I think it is. And so I think, yeah, it's a really interesting topic.
Got you. Got you. Thank you.
I had another question. I was wondering about, you mentioned, that the algorithms are driving so much of the social media content, and I wondered if you could infer changes in the algorithm based on what you're seeing in the network graph. And I was thinking this would be kind of analogous to detecting mutations that affected, the spread of something, if you were to look at it
Mm,
biologically. So I was just wondering if you're able to, if they make a change to how the news is propagating, can you actually detect and work backwards to infer what the change was?
yeah, that is a fascinating question. Um, right. So I think in theory, if I had the actual, so the big caveat here is the data. And so these companies are just like um, they're so guarded with their data. I remember, I don't know if anyone saw this, but so on social media, these researchers were basically, they made an extension for Chrome or something like this, and they actually had this exact question. They actually though wanted to see which ads you were being served. So basically, if you gave them access to your Facebook, it wouldn't actually, read your private messages. It would just skim and look for what ads were served. But actually, Facebook, I think, filed a lawsuit about that, or demanded that they like cease and desist. Um, so yeah, it's like pretty contentious. So that's kind of the background for all of this. Let's see. So I think, yeah, if I had information, so I think you said two things. First, can I detect? Well, first you said, what can I observe when I notice that the network is changing? That's an interesting question. And then I think you were also asking, like, how does can I infer how the news uh, feed has changed? Is that actually what you were asking, though?
Yes, yeah. So can you detect the change and then would you be able to infer what caused it? Like, what the
Yeah,
change is in the, yeah.
that's really interesting. So, um, I mean, unfriending is for sure a thing, and it oftentimes can be in response to, you're, sick of hearing people's rants about whatever on Facebook, for example. So there is this, going back to homophily, I think there is just like well documented examples of people cutting ties with people that have become too distant, like socially, from them. And so maybe that's like inflamed by the news that you're fed. Maybe it like serves to polarize you and kind of create two, like, or more rather, echo chambers. Um, yeah, this is a really interesting question. So I think it would be really interesting. So if I had both the news that were being served to the users, and then I notice the evolution of the social network, yeah, like, is there some causation there? That is such a fascinating question. I don't have a good answer for you, but it's certainly worth asking. Um,
Awesome. Well,
yeah,
thank you.
yeah. Thanks for the question.
Yeah, all right. So, Nicholas, we've been here for about 1 hour and 45 minutes now. It was really fascinating to have this discussion with you. We hope that we can invite you back here again in our group. And I just noticed that Damon Centola has been our guest speaker twice in an interval of
Oh,
only
really?
one.
That's awesome.
And the other topic that he talked about was about a tipping point, about
Oh,
tipping
really?
points. And yeah, I think our people, that was 2 years ago, the kinds of people that we have here, I think are 50% of those people are here now, and there are new people coming in this club. So, but
Wow.
yeah, we are a group that really, would like to, are very interested to hear studies and opinions from people like you. So I hope that we can invite you back here again in Quantum Photonics sometime soon. It
Yeah.
was really fascinating.
Yeah. Thank you, everyone. I just really appreciated talking with you all. And thanks for being patient with my newbie clubhouse skills.
What can you say about your first clubhouse experience
This was really
before?
fun. Yeah.
Yes,
Yeah.
so yeah, I hope anyway we can invite you back, and I'd
Yeah.
like to ask Bob if he has some message or comment before we start to wrap up.
Well, I wanted to say on behalf of everyone who's been quiet in the audience that this has been a great presentation and a fascinating discussion. So thank you very much.
Thanks, Bob.
Yeah, all right. Do you have some parting shots for the audience, Nicholas, before we finally wrap up?
Um, yeah, this is an amazing group, and I feel so honored to be here. Thanks, everyone.
Yeah, thank you again. And we'd like to tell everyone that we're having a room tomorrow. It's yeah, gonna be very interesting at about 4 p.m. Pacific time. So please be here. It's gonna talk about a new sport, but that a lot of us have never heard before, and the relations of neuroscience to it. So anyway, once again, thank you, Nicholas. It was really great. Let's flash our mic for Nicholas.
Thanks. And thanks for the invite, Cecile.
Thanks again. And now we'd like to give the mic to Darcel. And thank you, Lisa, Kevin, Shane, Ovi, Chavez, and Dr. Shilanch for being on stage. And everybody in the audience, I could not mention you all. Thank you so much for your support. I'd like to give the mic to Darcel now.
Yes, I echo everything that was said. Thank you, Doctor, for a great talk tonight. To start our countdown, we're gonna to close the room. We're gonna start from lucky number 10. Is everybody ready?
Ready?
Ready.
10.
Set.
10,
Dr. Salaj 9.
Nine.
Nine,
Chavez 8.
Eh,
Eight.
Ovar 7.
7,
Shane 6.
6.
Kevin 5.
Fiver.
Lisa Megawatt 4.
Cuatro.
Bob Trace.
tres,
Cecile Dos Equis.
two.
Good doctor, your numero uno. Call out our last number, please.
Uno.
Ha!
Yeah, thank you, Nicholas. See you back in Quantum Photonics sometime soon. And good night, everyone. See you in the next rooms.
Thanks.
Awesome, Nicholas.